So welcome. So we're going to do this fourth part of the first section, which is on waves, oscillation waves, standing waves, superpositional waves, and the like. And basically, we're going to do the last little bit, which is on superposition and standing waves. So what we're talking about? We're talking about when we get two sources of wave energy, or we get one source reflected back on itself. That would also work. We say if two waves occupy the same space, they can interfere with each other. They add constructively or destructively. When a family of waves are reflected back on themselves, those experience destructive interference quickly die out, and those that experience constructive interference sustain. An instrument such as a taut string or an organ pipe will support a family of waves that are harmonically related, and two waves with slightly different frequencies will produce sound that displays beats. So what are we talking about? We're talking about, we have a medium. Let's say the medium is a guitar string, and we put energy into the guitar string, and it manifests itself as waves. The wave energy goes outwards and hits the ends and comes back, and very quickly you get to the stage where the energy is just, if you imagine the two waves are just interfering with each other because it's trapped. That's one manifestation. The other manifestation is where you get two speakers, and basically there's waves coming out from one speaker and there's waves coming out from the other speaker, and depending upon where you are relative to the two speakers, you may find that the crests or the compressions arrive at the same time, always. So you get crest when you get crest, you get trough when you get trough. And if you go a little bit to the right, you may find that you get a crest when you get a trough, and a trough when you get a crest. And so there's always cancellation taking place. So there's these two scenarios, and our job today is to try and sort out what's going on with these kind of situations. So superposition of waves. So we're going to deal with it mathematically, and I don't need the math. I just need the understanding from the math. What we say is that when two or more waves move in the same linear medium, linear not meaning like a string, but linear meaning 2 + 2 = 4. It's like it's arithmetic sums. In the same linear medium, the net displacement of the medium, that is the resultant wave, that's the one down here, at any point, that's somewhere along here, equals the algebraic sum of the displacements caused by the individual wave. So imagine there's only one wave, and the first wave is giving me a point like that. There's my y displacement. And the second wave is giving me a point like that, 0. You add those two up, and you get that negative. And if I imagine here where I've got a maximum there, well, I don't have quite a maximum there. It's a bit to one side. So I end up with just a little positive. You can see the extremes, can't you? If I have them in perfect phase, then when I add them together, then I get 0 and 0 makes 0. And if you like, amplitude plus amplitude means two amplitudes. And then 0 and 0 makes 0. And minus amplitude with a minus amplitude makes two amplitudes. So you get a wave that's twice the amplitude, because they are in phase. And if somehow I could make it so that the one wave completely contradicted the other wave, then I'd get 0 adding with 0 to give me 0. I'd get positive amplitude adding to negative amplitude giving me 0. I'd get 0 and 0 giving me 0. I'd have negative amplitude and positive amplitude giving me 0 and 0. So this is destructive interference. You have two waves there. They're in there. The energy exists. But at that point in space, you see nothing. They are cancelling each other out. And you go to the other extreme where they're in phase and the amplitude doubles. And then you go a little bit in between, and this is a little bit in between, where they're kind of not, they're not completely out of phase. They're kind of like, how much out of phase are they? They're that much out of phase, you know, the base to the base. It's not quite, you know, the top waves, that's a wavelength for the top wave, and the out of phase bit is maybe, what, 2/3 of a wavelength out of phase. Then we get this weird thing. It's almost destructive interference, but it's not quite. I can draw diagrams like this, but can I mathematically do this? Consider two waves that have the same frequency, wavelength, and amplitude, and are traveling in positive x direction, so they're traveling in the same direction. So they both got a sine kx minus omega t because they're traveling to the right. But this guy is just a little bit of a phase ahead. So we have a sine kx minus omega t plus phi. So that's the only difference, plus phi. I got to remember some trig, I guess. Well, y equals y1 plus y2, which equals a sine kx minus omega t plus sine kx minus omega t plus phi. And then I remember a bit of trig. I say sine a plus sine b equals 2 cosine a minus b over 2 sine a plus b over 2, where a is equal to kx minus omega t and b equals kx minus omega t plus phi. And I don't need you to remember that. I don't remember that. It's like, but you put them together and you do substitution and you find that y, that is the y displacement of my answer, is equal to 2a cosine phi over 2. That's my phase difference over 2, sine kx minus omega t plus my phase difference over 2. The important thing is, if you plot this out, if you change your values of x and you plot this thing out, you get that graph. Okay, so if you want to see what the answer is mathematically, use that equation. I don't need you to remember that equation. I'd like you to know that it's around, but all I want to do is make sure you know it exists. I'd like you to be able to kind of get a rough idea from these diagrams. The resultant wave has the same frequency as the wavelength of the original waves, and I know that because omega's not changed. Okay, the same frequency. So it's got at the maximum. Well, it depends on the thing. You can't say that. Okay. This is a visualization of it. If we have these two guys in phase, so it's basically the same equation in both cases. We simply get twice that equation because we're just adding constructively. You take that peak, add it to that peak, and you get that peak. You take that trough and you take that trough and add it to that trough and you get that trough. And if I take to the other extreme, so this is constructive interference. So there's a terminology to be comfortable with. And then we have destructive interference. And the only difference with destructive interference is that the crest or the compression coincides with the trough or the rarefaction. You know, we get zeros. So we get that. And mathematically, you can see it because, well, you go from a crest to a trough by jumping ahead or behind by half a wavelength. Yeah, think about it. There's a wavelength. If I go from a crest to a trough, that's lambda over 2. And lambda over 2 is pi radians. So in this phase angle, when that phase angle is pi, and we add them together, we get 0. So. Now, when they're in phase, we call them in phase, and when they're perfectly out of phase, not when they're a little bit out of phase, that's when they're a little bit out of phase. That's a little bit out of phase. But when they're perfectly out of phase, we call it antiphase. Okay. So, imagine a situation. We have a speaker in one corner, a speaker in the other corner, and the sound coming towards me. The sound is constant speed because it's the same air. The speakers are themselves in phase. What that means is they push at the same time, pull at the same time, push at the same time, pull at the same time. They cause a compression wave, they cause a refraction wave, they cause a compression wave, they cause a refraction wave at the same time. Yeah, in sync. I'm equidistant between those two speakers. When one compression hits me, the other compression hits me. When one rarefaction hits me, the other rarefaction hits me. So I am in phase. I will hear twice the sound, twice I'll get twice the pressure amplitude of sound. Or if you want to imagine a swimming pool, perfectly level swimming pool, and there's two little wave machines, and they send ripples towards me. I'll get the ripple from one with a ripple from the other, and I'll get a ripple twice as big in my face. Yeah? Because the distance is the same, and the speed's the same, and they started at the same time. It's a bit like soldiers marching towards me. If they start marching at the same time and then the same distance, they're going to go step, 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 and they're going to arrive in phase. You know? Bang, 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 bang. They're going to hit me in phase. Here's a trick, though. I can move a little bit to the right or the left. And at first, there'll be a bit of a mess. But then I get to a situation where I'm still getting a crest with a crest or a compression with a compression. But I'm not in the middle point anymore. And what's going on is, if you imagine it takes 10 steps to get to me for that soldier. When I was in the middle, it was 10 and 10 steps. Yeah? They arrived at the same time. Now, it's, if you like, 10 and 11 steps. But they still arrive in time because they go, you know, step 1. They both arrived at the same time. One took 11 steps, the other one took 10 steps. But they both arrived at the same time. So there might be 11 crests between me and that little wave machine. There might only be 10 crests between me and that little wave machine. But the crests arrive at the same time. And I can go over here, and now it might be 9 and 11. But the thing is that the crests arrive at the same time. And it might be, 8 and 13. They still arrive at the same time. There's these points where I will get constructive interference, not just in the middle, but in all these places. And the key is that the path difference is a whole number of wavelengths. I don't care if I'm getting the 13th crest with the 11th crest or the 9th crest with the 4th crest. What counts is I'm getting crest with crest. And I'll get that when the path difference is a whole number of wavelengths. And I can show you that on this next diagram. So here's a snapshot. And I'm showing, in blue, I'm showing crests. And in green, I'm showing troughs. And so I took a picture. And here's my first ripple. I'll find my pen again. Here's my first ripple. And there's my second ripple. And in between, there's a trough, yeah? Question or comment?
Yes, sir. I have experience, I'm sure everyone else here has, having two televisions on simultaneously with the same channel tuned in. Now, in that instance, depending upon your position, you can either have an amplification of the noise or an actual echo. With the example that you just laid out, where one sound wave approached you at 9 and another sound wave approached you at 11, is that the circumstance you're attempting to depict to us, or?
I don't know what you mean by an echo or I don't know what you mean by your example.
Delay where surely everyone else here has experienced at some point in their life where they've had a delay between.
We're not talking about a delay because we're talking about, there is a delay, but we're talking about a perfectly repeating phenomenon. And so the delay becomes irrelevant if it lines up. So it's not like the soldiers are counting, 1, 2, 3, 4, 5. They're just going step, 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 step. And the thing is, if they both arrive and say step, then they're in phase. Okay? So I think.
Right.
Okay. So if we look at this, in this middle bit here, I got a trough arrives with a trough, and a crest arrives with a crest, and a trough arrives with a trough. Anywhere on that line, I have that situation. And so that would be constructive. Now, over here, I have a crest arrives with a crest, and a trough arrives with a trough. And I didn't draw it, but a crest arrives with a crest. So that also would be constructive. And down here, I'm different distances, but I'm getting a crest with a crest and a trough with a trough. And I didn't draw it, but it's a crest with a crest. So that would also be constructive. And the situation about those is you get constructive interference when the path difference is, I want to say, a whole number of wavelengths. But I'm going to say it slightly differently. I'm going to say an even number of half wavelengths. Now that might seem like, why on earth would I say an even number of half wavelengths? But there's method to my madness. On the same diagram, but now if you look over here, at this point, I have a crest arrives with a trough. 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 That's destructive interference. That would be calmness. I have a crest arrives with a trough, a crest arrives with a trough, a crest arrives with a trough, a crest arrives with a trough. That's destructive interference. Now, what's happening there is the path difference for destructive interference. The path difference is an odd number of lambda over 2. Because, you know, in the time you have available, from there to here, I have a different distance from there to here, and the path difference is, in some cases, an even number of half wavelengths, and in other cases, an odd number of half wavelengths, sometimes in between, but I'm only going to deal with those. And when it's an even number of half wavelengths, I get twice the amplitude. If it was a sound system, I hear loudness. And if it down here, I'm going to get a destructive interference. I would hear silence or quietness. And I don't notice it in things that change in time. And I actually don't notice it in modern music or any kind of music, because it's too complicated. Different frequencies have different wavelengths, and so it's what works for one frequency does not work for another frequency. But if I have a single frequency, a hum coming out of the two speakers, and I move from place to place, man, I can hear loudness, and then I hear quietness, and I hear loudness and quietness. I can hear it. And I can actually show you this. I have to do a little bit. I'm sorry, I meant to dig this up beforehand. But let's just see if I can find it. And I had one perfectly picked out on the old system, and then when I transferred over to the new system, I didn't bring it in. So let's go here. And let's try, we're going to have Ripple Tank. Ripple Tank experiment, I'm going to do that. And then I'm going to go to videos. And if I can find it, let's have a look. I think it's that one. No, it's only short. Let me just have a quick look a bit longer. Ripple Tank, because this was quite a... let's put historical. Because there's one that I'm familiar with that is just really nice. Let's do one more. It may have been taken down. Let's go back. I can get you some idea of it anyway. So let's do that. And then let's pick out one of these. Experiments, YouTube. This might be it, actually. Let's have a look. So this is kind of like the Ripple Tank. It's just basically showing you a wave going forward and bouncing back. And it's actually, it's a complicated light system, but you can see the energy travels. And then there's a family of waves come in. Yeah, boom, boom. Let me just jump, let me just see what's coming out. Because I don't want to spend 21 minutes on this. So this is reflection off a surface here. Some waves come in, and you see they bounce and they go off like that. Let's jump ahead. So again, there's a reflection taking place. This is not the one I was thinking of, but it'll be all right. So okay, yeah, we get the idea. So it's a family of them bouncing off. And then reflection from a palligraphic barrier. So this is the focusing. So the wave comes in. I'll show you. The wave is going to come in from the left. It's going to hit there. Oh, I missed that. Let's just see if I can grab it. So the wave is going to come in. Oh, I see. They're taking the wave from here, and it's reflecting out as a nice plane wave. So I think the wave's going to come in now. Yeah, the wave comes in, and it goes to the focal point. Boom, and it hits at the focal point. Here's some family of waves coming in, and you can see it's like it's building up there. Can't you see it? It's building up there. That energy is building up right there, because that's where the focal point is. And this is probably going to show you different. I'm going to put a wave in here, blop, 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 and watch the ripples bounce back. Yeah. Let me have a look. I want to try and get ahead. No, they're doing fancy stuff that I don't really care about. Superposition, yeah. Single pulses. Intersection of the pulses depends upon the relative time and the origin of the pulses. Come on. So notice, look, these guys are interfering. At some bits you're getting so there, at that point, there's a line of constructive interference. They're kind of showing it with that line. And then hopefully they'll do families.
So, I think that the antiphase, is that conditional upon the time in which the other wave is emitted?
It just,
Because I need to have a negative trough.
they're going to go crest, trough, and where you stand depends on what combination you get. You might get crest and crest if you're in one place. You might get trough and trough in another place.
Right.
So if you look here, so you can see that you can get constructive interference if they're slightly out of phase, going off at a line. I want to just... So now they're beginning to show it, where you go, oh, come on, let's get on with that. Yes, at last. Can you see constructive interference, destructive interference? There's like a little null bit there. Constructive interference, destructive interference. Constructive interference. Can you see that? The constructive interference bits tend to be what you see, what your eye's drawn to, and they look bigger. The destructive interference look like these narrow passageways, but that's a function of the light intensity doesn't go perfectly with the wave dynamics. So very clearly, you can stand here and you will hear a loudness. You can stand there and you'll hear quiet. You can stand there and you hear loudness. You can stand there and you hear quiet. So what's going on is it's the path difference, because these guys are in phase. I'm not sure if they're going to switch phase. That's again, now what they're doing is they're talking about destructive interference and constructive interference. They've changed the frequency though, and then they're going into diffraction effects. Okay, I don't need any more of that. As I say, I used to have one in my old layout, and I need to bring it back for the new layout. So I need to stop you, because otherwise you're just going to be using power up, and that's what I'm trying to draw here. Okay, so we're going to do from beginning and go boom, 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 boom. So that's what I'm trying to get across there. These regions of constructive interference, So these regions are constructive interference. And then these regions are destructive interference. Okay. So two speakers are in phase. Listener stands equal distance from each speaker. What would she hear? Would she hear silence because they're destroying each other? Would she hear loudness because they're supporting each other? Would it be that silence with destructive interference, or silence with constructive interference, or loudness with constructive and loudness with destructive? Speaker, speaker, listener. These guys are in phase. So which one do you think? Anybody want to suggest? It's going to be loudness, and it is going to be constructive interference, because you get things adding together when you get constructive interference. Agreed? Let's be a bit more formal about this. I'm going to imagine a distance to my listener from speaker 1 and from speaker 2. I'm going to say, suppose we have two sources of waves that are in phase. Let us assume that the waves from each source interfere at point P. The path length from source 1 to P is R1, source S2 to P is R2. At one extreme, if the path difference between R1 and R2, if the difference in length is half a wavelength, is an even number of half wavelengths, then we will get constructive interference. So we get even lambda over 2, we get constructive. For destructive, we get an odd lambda over 2. And you can think about these in terms of wavelengths. On the other hand, you can think about them in terms of phase angles. And I can represent half a wave as half a circle. So that could be an even pi radians, and that would be an odd pi radians. I'm saying the same thing. That is the same as that. I'm just taking from pi bin, a wavelength bin 2 pi radians, half a wavelength is pi radians. And I can even talk about it in terms of an even number of 180 degrees and an odd number of 180 degrees. It's all saying the same thing. Agreed? So how do I figure what's going on, say, in radians? Okay, my phase difference between the two waves that are coming. What's the phase difference between the two waves that are coming? My phase difference is the path difference in meters divided by the wavelength. That gets me the fractional, the distance in wavelengths, multiplied by 2 pi gets me the phase difference in radians. I don't remember that equation because I can always figure it out. Let's just do an example. So the interference of two sound waves that are in phase. So these guys are in phase. They're not always going to be in phase, but I'm starting off with them in phase. This is 2.8 meters, and this is 2.2 meters. And the wavelength is equal to 0.4 meters. So my path difference in meters is 2.8 minus 2.2, which equals 0.6 meters. My path difference in lambdas is 2.8 minus 2.2 over 0.4, which equals 0.6 over 0.4, 0.4, which equals 1.5 lambdas, which equals 3 over 2 lambdas, which equals 3 lambdas over 2. Now, can you tell me from that, is that constructive or destructive interference? It's destructive because I have an odd number of half wavelengths. Yeah? So I worked out my path difference, and I said, I wonder how many wavelengths that represents. Divide the path difference by the number of wavelengths, by the length of a wavelength, and you get this 1.5 wavelengths, which is 3 over 2 wavelengths, which is 3 half wavelengths, which is destructive. So I've decided it's destructive already. If I want, I can talk about this in terms of my path difference in radians. And that I can say is it's going to be 2.8 minus 2.2 over 0.4. That's given me my path difference in wavelengths times 2 pi, because each wavelength is worth 2 pi radians, which equals 0.6 over 0.4 times 2 pi, which equals 3 pi. And it's an odd number of pi radians, so destructive. So can you see how, yeah, if you look at that expression, that's saying that pi is equal to R1 minus R2 over lambda times 2 pi. That was the equation we just had, but I don't have to remember it. I can just figure out where it's coming from. The book does tend to do an awful lot of equations, and some of them you can just figure out. So that's the name of the game, basically, that I play. So this is a little thing to remind you that one wavelength is like 2 pi radians, which is like 360 degrees. There's one wavelength. And to go from there, I go to the top, and then I go back, and then I go to the bottom, and then I come back. So that's 2 pi. So that is 2 pi rad. And you could also say that that is 360 degrees. So just to remind you of those 3 ways of talking about the same thing. If the wave sources are not in phase, we must consider the phase difference in addition to the path difference effect. So I could have my wave, one wave like that, and the other wave could be like that, so that they don't line up really good. So now I have a path difference, but I also have a phase difference of my speakers. In this case, the phase difference is 1 pi. What that means is it's half a wavelength out, which means that when one's pushing, the other one's pulling. So these are antiphase. If the total effect isn't, so what I do is I look at the total effects. So I look at my phi, which equals my path difference phi plus my phase difference phi. I can do that. I just add in. Before, when they were in phase, there was nothing to add. Now I've got a bit of phase difference in my speakers. But the answer is still the same. If it's an even number of half wavelengths, then it's constructive. If it's an odd number of half wavelengths, it's destructive. Or an even number of pi is constructive, or an odd number of pi is destructive. So here's an example. Interference of 2 sound sources. This is 2.9 meters, and this is 2.5 meters. And my lambda is equal to 0.4 meters. And I say that my phi is equal to my path diff phi plus my phase diff phi. So my phi is equal to, well, my path difference phi, well, that would be 2.9 minus 2.5. That's my path difference in meters, divided by 0.4. That's my path difference in wavelengths, times 2 pi. That's my path difference in radians. Plus, and I was told up here that this is 1 pi, so that's going to be pi. If you like, well, let's just finish this off and then we'll talk about that. So this is going to be 0.4 over 0.4 times 2 pi plus pi, which equals 3 pi. Is this constructive or destructive interference?
Destructive.
3 pi rad. It's an odd number of radians, so that's destructive, yeah? Agreed? The path difference would have given you even number of radians. That would have been constructive, but because of the phase effect in the speakers, it got changed. If you want, you can do a lot of this, talking in terms of wavelengths. So I can say my lambda end is equal to lambda path difference plus lambda phase. So my lambda path difference, I'll do it over here. So my lambda end is equal to lambda path difference plus lambda phase. So my lambda end is equal to, my path difference lambda would equal 2.9 minus 2.5. That's the distance in meters over 0.4, which equals 1 lambda. I'm sorry. Plus, I'll figure that out in a minute. Lambda. Plus, for the phase, it's half a lambda. Lambda over 2. So lambda in the end is equal to 1 lambda plus 1/2 a lambda, which equals 3 over 2 lambda, which is destructive interference. I can convert this, so this becomes 3 over 2 lambda equals 3 over 2 times 2 pi, which equals 3 pi rad. So that is the same as that, because it's the same problem. We're just doing it in 2 different ways. So my advice is, especially when you begin, pick one of them. I'd pick radians and stick to it, or I'd pick wavelengths and stick to it. And then do the conversions to go backwards and forwards. Cool. How am I doing for time? We started at 2, so we've done 45 minutes. I'm going to just do a 5-minute break. So let's just...